Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. We are in Unit 4 talking about applications to the derivative. And this is section 4.3 talking about the first and second derivative tests and the tests for concavity. So I wanted to do a new video about the second derivative test for local extrema only because often students confuse these two tests. So the test we just did in the last video, the first derivative test, where we look to see the change in the sign of the first derivative, is a way to find local extrema, or local minimums and maxima. The second derivative test can also be used. Now, the second derivative test actually finds the same thing. So this is just a different way to do the same thing. If you like the first derivative test, you can stay with the first derivative test and you don't even need to know this one. However, the second derivative test you'll find as we move forward might be simpler to do as long as the second derivative is an easy thing to take. So the second derivative test for local extrema says this: we can find local minimums and maximums of a function by using the second derivative. And this is how we do it. If the derivative at a certain point p is equal to 0, in other words, if p is a critical point of the function f, and if the second derivative at that point p is positive, well, we know from our shortcuts that when the second derivative is positive, we know the original curve is concave up. If the original curve is concave up, then we know that that critical point must be happening at a local minimum point at p. If the first derivative at some point p is equal to 0, in other words, so if we have a critical point at a point p on the original curve, and we know the second derivative at that same point is negative, then we know that the original curve must be concave down. And if the curve is concave down, the critical point will occur at the top, or where the curve has a local maximum value. So the second derivative test actually helps us determine the extrema by looking at the concavity of the curve at that point. If we have a critical point, a point x equals p is equal to 0, the derivative is equal to 0, which means that p is a critical point of the curve, and the second derivative is also 0, then this doesn't tell us anything about extrema, but it will possibly tell us where the curve will be changing concavity, or in other words, it will possibly give us possible points of inflection, but it will not tell us anything about whether it's an extreme. In order for the function to be an extreme, the curve has to either be concave down or concave up, and if the curve is neither, here you can see where the second derivative is 0, which means we're neither concave up nor concave down, then that will not tell us that that point is an extreme. In other words, if we put critical points into the second derivative and the result is a positive result, then we know that that critical point must have been a local minimum. If we put the critical point into the second derivative and our result was a negative number, then we know that that critical point must be locating a local max on the original curve. This is the second derivative test for local extremes. Let's go back to the example we are looking at and show you we already knew what the answers were. We found those answers using the first derivative test, but I'm going to use the same equation, but now use the second derivative test. So the procedure for the second derivative test is, first I find the critical points. So I find where the first derivative is equal to 0. Well, I already did that from the last example. Those were at x equals 0 and x equals 2. Now, what we do for the second derivative test is we simply find the second derivative and we put those possible extremes, x equals 0, into the second derivative. If I get a negative value, that tells me at this critical point of x equals 0, the curve is concave down because the second derivative is negative, which means if the curve is concave down, that critical point at x equals 0 must locate a local max. Because the second derivative at x equals 0 is negative, the graph is concave down. Therefore, the point 0, 4, again, where did I get the 4 from? This is a point on the original curve, so I put 0 back into the original curve to get the point on the original curve, must be a local maximum. Now I do the same thing with the other critical point that I found. I put in 2 and I find a positive value. So because the second derivative is positive at this critical point, that means the graph must be concave up there. And if the curve is concave up, then the critical point that I found must be a local minimum at the bottom of that concave up region. Therefore, the point, and again, that point on the curve, I went back up to the original curve to find the point on the curve, is 2, 0, must be a local minimum. All right, that is the second derivative test for local extremes. Now next, I'm going to show you the test for concavity, or this is called the concavity test, or looking to see where we have points of inflection, where the concavity may change on the original curve. This is called the concavity test. When we look for points of inflection, what we do is we set the second derivative equal to 0 and see if the second derivative changes sign. So this is called the concavity test. We are looking not for extremes, but points of inflection. We set the second derivative equal to 0. This is not called a critical point because critical points are only points when the first derivative is equal to 0. Now, many books call this point a key point, or other books call this a possible point of inflection, is where the second derivative is equal to 0, are called possible points of inflection, or key points. Next, what we do is we say, okay, this is a possible point of inflection at x equals 1, where the second derivative is equal to 0. Then what we do is very similar to the first derivative test. We put that value of x that we found a possible point of inflection on a number line or on a chart, and we say, okay, when x equals 1, the second derivative is 0. That now divides the domain region into two regions, that's less than 1 and that is greater than 1. And we test in each region into the second derivative for possible points of inflection. So I pick a point over here, say at x equals 0. I put it into the second derivative and I get a negative value, which means that the original curve is concave down on that region. Then I pick a point on the other side of the possible key point or possible point of inflection, and I get a positive value. So what does this tell me? This tells me that the curve is negative here, which means that the second derivative is negative here, which tells me the original curve is concave down until 1. And then from 1 to infinity, the curve has a positive second derivative. So that means my curve is concave up. So that means my curve was concave down until I reach 1, then concave up after 1. Therefore, x equals 1 must be a point of inflection. If there's any change in sign, doesn't matter which way, negative to positive, positive to negative, doesn't matter. If there's any change in sign, then there's a point of inflection at that point. So there is a point of inflection at x equals 1 because the second derivative changes sign. Positive to negative doesn't matter, negative to positive, but simply the second derivative is changing sign. So what we're going to do here is put all this information that we had together with all the different things we had. When x was equal to -1, the value of the curve was 0. The value of the derivative was positive, and the value of the second derivative was negative. So what does this tell me? This tells me the point -1, 0 is on the curve. The curve must be rising because the first derivative is a positive value, and the curve must be concave down because the second derivative is a negative value. So let's plot that point on the curve. Let's pick another point at the local max we knew that the point 0.04 is on the curve. The derivative was 0, which made it a critical point there. And the second derivative was negative, which made that critical point a local maximum. So let's put that point on the curve. Next, we had the point of inflection. At the point 1, 2, which is the point on the curve, the first derivative was negative, which we really didn't care. We just know that the curve is falling there. And the second derivative was 0. But we found a point of inflection because we found that the second derivative was changing sign around this particular point. Next, we found the point 2, 0, the other critical point. This critical point at 2, 0 was a local minimum because the critical point, we know that we have a critical point here because the first derivative is equal to 0, and the second derivative was equal to a positive value there, making the curve concave up, making that critical point a minimum value. Now you can also see here from my table of values, the derivative is changing from positive to negative around this critical point, therefore making it a local max by the first derivative test. And then lastly, we pick another point on the curve. I just picked another point at x equals 3. The first derivative is positive there. The second derivative was positive also, which tells me if the first derivative is positive, the curve is rising. If the second derivative is positive, the curve is concave up. Now again, we can see by the first derivative test, this critical point, when the first derivative was equal to 0 at the point 2, 0, you can see by the first derivative test changed from a negative derivative to a 0 derivative to a net positive derivative. So changing a derivative from negative to positive is also a local min by the first derivative test. But we were using the second derivative test there when we looked at the curve itself. So let's just connect the dots. There we go. There's our cubic with all the strategic points on the curve. The local min, the local max, the local max, the local min, and the point of inflection. And then I just picked 2 other points on the curve to finish off my curve. All right, so let's try to do a couple more of these by hand. In this case, I would like to use the first derivative test to find the extrema, to find the local mins and maxes. All right, so what's our procedure? First, we take the first derivative. We set the first derivative equal to 0 to find critical points. Here's a little bit of algebra here. I split the middle term to factor this expression. So my critical points occur at x equals 4/3 and x equals -2. Critical points occur where the first derivative is equal to 0 or the first derivative is undefined. In this case, my first derivative was a nice, easy function that I could factor easily. As we move forward, we're going to be using Mathematica because our functions won't be so easy, and we're going to be able to have Mathematica to help us to find those critical points. So I have critical points there of the original function. So now I drew a number line, and I put these critical points on the number line. So I had a critical point at -2 and a critical point at 4/3, which is 1 1/3. Then I test the regions that's divided by this critical point. So I'm going to test below -2, any number below -2, between -2 and 4/3, and anything bigger than 4/3. And I'm going to test it by looking at the sign of the derivative because this is the first derivative test. Notice I'm labeling it with the first derivative. So I found my critical points. I tested over here. I picked a number -3. I put -3 into the derivative and I found a positive value. So that tells me in this region I have a positive first derivative. Then I tested in this region between -2 and 4/3. 0 is the easiest there. I put 0 into the first derivative and I got a negative value. Again, it really doesn't matter what the number is. We want to know what the sign of the derivative is. And then I'm going to test over here in this region bigger than 4/3. I'm going to put in -2. When I put -2 into the derivative, I get a positive value. That means my derivative is positive, then negative, then positive. Therefore, at x equals -2,